Okay, this is lecture 9, where we're going to talk today about convection and mass transfer. And here's just an example of convection with the wind blowing on the clothes and no convection. And of course, in this instance with convection, they're going to dry faster. And that's because the fluid is flowing past the solid surface of the clothes and taking away the water that has evaporated out of them. So the concentration gradient is higher and it dries faster. Today we're going to learn about what is convective mass transfer, what is the convection coefficient, and how to estimate them. So convection can occur between a moving fluid and a surface, like the clothes, or between two immiscible fluids, like the fluids in a lava lamp. We're just going to talk about a surface today, moving fluid and a surface. So we'll start off with something simple, where we've got fluid flowing over a flat plate. And here's the fluid flow right here. And diffusion is coming from something is diffusing out of the flat plate and into the flow, into the liquid. The V infinity term is the velocity of the fluid infinitely far from the plate. That means it's far enough that it doesn't feel the effects of the plate. It doesn't have to be infinitely far, it could only be a centimeter or so away. This is the velocity profile right here of showing the velocities of the fluid right up next to the plate. And you notice right here the velocity is 0 because the molecules right up next to the surface of the plate are moving with the same speed of the plate, which is 0 in this case. That's the no-slip boundary condition. So we go from 0 and it has to increase up until it gets to V infinity, and then it becomes constant. That was the velocity profile. We can also have a concentration profile for the fluid that's going past this plate. So in this case, the concentration at the surface here is greater than the concentration infinitely far from the plate, which means, as I said before, that diffusion is going from the surface into the liquid, into this, not a liquid, a fluid. Could be a liquid, could be a gas. The concentration right up next to the surface is high and decreases as we increase in distance away from the plate.
And that makes sense, because if I think about the case where you've got, say, maybe a tablet you want to be dissolving and you've got fluid flowing over it, maybe saliva or something, then it would be most concentrated right up next to the tablet, and then as you go further away, there's less and less of maybe the medication.
And if we look at the concentration of the surface minus Ca, it's this profile here, which is exactly the same as this one. It's just flipped because we have a minus Ca. It's the same thing though. So now that we have convective mass transfer, this is the expression we're going to use, where Na is our mass transfer flux, just like we had before. This is our difference between the boundary surface concentration and some concentration, which is an average or so for the fluid. For a flat plate, we use Ca infinity. And that gives us our convective mass transfer coefficient, K sub C. Okay, and units of length per time. So as we're thinking about fluid going past a flat plate, for example, or any surface, but a simpler flat plate, there's a boundary layer that's sometimes extremely thin, very close to the surface. And this boundary layer, you have got diffusion going through this layer, and that's playing a large role in convection. If the fluid flow is laminar, meaning that the flow is well organized, the flow is slow enough that viscous forces can keep it well organized, then all of the transport is by diffusion, but we still relate it with the convection coefficient. If the fluid flow is turbulent, then the fluid is well mixed because you've got eddies going on in turbulent flow. And we'll also present this with a convection coefficient, but it'll be a little different because you've got a higher mass transfer rate if it's turbulent as opposed to laminar. This is just to relate the diffusivities. We've already seen mass transfer diffusivity with the units of centimeters squared per second. Similar to that is momentum diffusivity, which is just, this is a nu, is the viscosity divided by the density of the fluid. And it gives you the same units. And this is a thermal diffusivity, alpha. And it's the conductivity divided by the density. It's not working. The density and the specific heat. So we'll be talking about the thermal diffusivity in class when we get to heat transfer. Right now we're just going to be considering these, but I just wanted to show you how there's a symmetry between mass transfer, momentum transfer or fluid flow, and heat transfer. We have several dimensionless parameters that will be very useful to us. The first one is the Reynolds number. The Reynolds number is just some characteristic length times the velocity divided by the momentum diffusivity, or the kinematic viscosity. And it's a ratio of inertia to viscous forces. So if that ratio is low, so we have a low Reynolds number, then we get nice ordered laminar flow because viscosity is ruling. If it's high, then we get turbulent flow because inertia is ruling. Two other useful dimensionless parameters are the Schmidt number. The Schmidt number is just the ratio of the momentum diffusivity to the mass diffusivity, nu over the diffusivity. And since the units of both of these are the same, then the Schmidt number is unitless. The Lewis number is basically the same thing, but for heat transfer. So it's the thermal diffusivity divided by the mass transfer diffusivity. And once again, we'll use this in heat transfer. And the final one that we'll talk about is the Sherwood number, sometimes called the Nusselt number, mass transfer Nusselt number. It is the convective mass transfer coefficient times some characteristic length divided by the diffusivity. So it's a ratio of convection to diffusion.
And will these three dimensionless parameters show up a lot in these kinds of equations when you're working these problems?
Yes, they do. They're very useful. And the beauty of them is that the dimensions, once you get them, work through the units for them, the dimensions are gone.
And that's handy because we don't have to worry about figuring out the units.
My voice is going too. Okay, so let's go back to the flat plate. We've seen this before. In this case, the mass transfer between the surface and the fluid may be written as this expression. Nothing new here. Here's the mass transfer flux, the convection coefficient, and the difference in concentration. Okay, and here it is again. Now, we can also write that using Fick's first law. It's minus the diffusivity times the gradient at y equals 0. And since the concentration at the surface is constant, I'm just going to plug it in there. And that doesn't change this expression here. They are the same. And now I will take this expression and equate it to this one to get this expression right here.
And that bit with fixed first law is basically lectures 4, 5, 6, and 7. If you'd like to go
Well,
back and see where that came from.
Fixed first law is lecture 1. Okay, so I'm just rewriting that. And now I'm going to rearrange it. I'm going to take this over here to get this expression. And so here, I'm almost assured the Sherwood number. I just have to multiply by some characteristic length here. And I did that here. Oops. I divided on the bottom so it comes up to the top. And I get the Sherwood number. Okay, which we looked at before. Anyway, this is just illustrating how it is a ratio of diffusion to convection. So where do we get these mass transfer convection coefficients from?
And for context, is this where do they come from? Is this like, let's peek behind the scenes for fun?
Yeah.
Okay, so
Yeah.
less worries about this being on test, but sort of behind the scenes of knowing where the thing come from.
Right, right. So you'll never be asked to do this exact analysis. Maybe you might do something like that for the fluid mechanics when you get to it, but not for the mass transfer. So people have done the exact analysis for a flat plate and laminar flow, and we have that. For other flows, they've done an approximate analysis, and for even more flows, they just went to the lab, found experimental data, and found experimental relations. And you can find whole lists of correlations to give you the Sherwood number from the Reynolds number and the Schmidt number.
Thank you, scientists from the past.
And yeah, and other things too, but we're just focusing on this. Okay, so yes, you have a question?
Oh no, I was just wondering if we were going to do this for the recap, so I guess so.
Okay, so for this example, this comes from an exact analysis, but you don't need to know where it comes from, just so that you have an idea where it comes from. If you have laminar flow parallel to a flat plate, and for a flat plate, laminar flow means that your Reynolds number is less than 200,000, then you can use this expression here. And it relates the Sherwood number to the Reynolds number and the Schmidt number.
And this is just magical math that someone else did for us. Thank you, whoever they were.
Right, to vastly simplify our work. So I want the local mass transfer coefficient at a point X, because that mass transfer coefficient does change as you move downstream from the front of the plate. So I want it at some location X. First, I'm going to calculate my Reynolds number using X as the characteristic length. V infinity is how fast the fluid is flowing, and nu, it comes from the properties of the fluid. Here's the properties of the fluid, and here's the diffusivity of the solute through the fluid.
So we've got that equation having the Sherwood number on the left and the Schmidt as well on the right. Oh,
Right.
and the
Reynolds number.
in the middle.
Right. And everything's unitless. So once I get the Sherwood number, now I know X, I know the diffusivity, so I can now solve for my convection coefficient. That is, by the way, at location X. If you want the mean from 0 to L, then the relation is just a little bit different. It's actually twice the other. Only now the Reynolds number is based on L as the characteristic length. The Schmidt number doesn't change. Nothing else changes. V infinity doesn't change. Then I can find a value from this relation using my Reynolds number and my Schmidt number. I can find the Sherwood number. Now I know the Sherwood number. I know the L, the position where I want it. I know the diffusivity, and I can find the mean coefficient, convection coefficient from 0 to L. If you have something besides the simple laminar flow over a flat plate, then you can come to this particular table gives you a few things. If you have a flat plate, if your Reynolds number is less than 200,000, these are the two relations that we just talked about. All right. And notice the Reynolds number is based on X. So as you increase X, as it flows down the flat plate, the Reynolds number actually increases. So if the plate is long enough and you get to a Reynolds number of 3 million, then you're definitely turbulent. Between 200,000 and 3 million is transient. It's transitioning. If you're over 3 million, you can definitely use this.
And that makes sense, because if you think about fluid flow, as it comes out of the origin, if it's nice and smooth, then as it goes on, it starts tumbling around itself more and more. So maybe think about water coming out of a faucet, how it becomes more and more turbulent and spattery as it gets further down away from the faucet spout.
Yeah, but that's something else too. It's also falling.
That's true, and it's not flowing over a flat plate, but
Yeah.
trying to just kind of visualize what this fluid looks like as it's going.
Yeah, it's the same visual thing, yeah. If you want to, what do you do between 200,000 and 3 million? I would say you could just use 200,000 as your transitional value, and you could go ahead and use this here. We'll see if Dr. Babincy agrees with me. Okay, so this one here gives you the local convection coefficient, and this one gives you the mean. And notice there are two terms. This first term is where they integrated from 0 up until you reach the transitional Reynolds number, which is here. Can we blow this up? Yeah.
Yep.
Okay. And so this is the laminar. This one is the laminar part, and this one is the turbulent part.
I'll label that. Turbulent.
So once again, the question is, what turbulent Reynolds number do you use? What Reynolds number do you use for the transitional Reynolds number? And I am saying that you can go ahead and use the 200,000. Dr. Babincy may have a different opinion, but she will tell you if that's the case.
Yep, and I think that goes to show something you've noticed in class already, which is that there are different approaches for solving these problems, because what we're doing is we're mathematically modeling systems, and sometimes there are multiple ways to do that.
Exactly. If you have flow inside of a pipe, it's laminar if the Reynolds number is less than 2,300, and the Reynolds number is the characteristic length for that Reynolds number is the diameter of the pipe. And this is the form of the relation here that you can plug in order to find your local convection coefficient. And these are some forms that you can use to find the mean. All right, and for the mean, you may have to calculate the Reynolds number based on R, and the Schmidt number, and R over the distance to see if it's either greater than 10 or less than 10, to give you an idea of which one of these relations you need to use.
And R here being the radius of the pipe?
Yes. Okay. If there's no subscript on the Reynolds number for a pipe, then you use the diameter. In this case, it's Reynolds number sub R, so it's the radius. And of course, if it's turbulent, then you've got additional correlations that you can use. And you're not limited to these. There are many correlations for flow over a sphere, for flow over the outside of a tube, for flow over a bank of tubes, as just a few examples. Okay?
And as I'm looking at these equations, I'm thinking about, the importance of knowing what each of these terms stands for. Because, right, over here you've got RE, which is Reynolds number, and we've got diffusivity here, but I think diameter there.
Diameter, yes.
Right, and so making sure that you don't mix up which term is which is why one of the suggested steps in Lecture 4 as a procedure for solving these kinds of problems was creating a little dictionary for yourself of what terms you're using and which variables you're using for which term.
Mm-hmm. Okay, and that's basically it. That's what we've done. Okay.
Yep, and so you met your friend, the dimensionless parameters today.
Yes, yes. These are your friends. Engineers love dimensionless parameters. Dimensionalize as much as you can.
All right, and that is Lecture 9.